Hello and welcome to this walkthrough of all the approaches for our hackathon submission. My name is Vijay, I'm IMT201955 and my teammate is Prasanna who is IMT201960 and our team name is the Carcarians. So as you know there were two tasks, regression and classification. Let's start with the regression task. So we did some pre-processing at first. We made box plots to detect outliers and then after box plots we also further analyzed these suspicious columns through KDE plots and through histograms, and those are also used to remove the null values and the duplicated values. And then we scaled things. So, for example, min max scaling is x minus max by max minus min, and then you have to reverse that scaling later on, and also standardization, which is x minus mu by sigma. So these mu, sigma, max, min are pertaining to that particular column x lies in, and then we split it to train and test. And then we trained a model on this data, and then we tested the model. So we had like alpha beta testing. So alpha testing was for this, and beta testing was for Kaggle. That is what we did with the data, and then we used some models to fit this training data, which is linear regression, lasso, ridge regression, and also polynomial regression. So that's multiple linear regression. We did linear, and so these are like the norms, lasso and ridge. And then polynomial regression, we tried to fit it for the number of polynomials, which is 220. The ideal we got, I think, was 9. All of these findings are included in our report as well. We also tried a few new things during the hackathon. This first is support vector regression, or SVR. What is SVR essentially does is, so let's say this is the points, these blue dots, they could actually form plane or hyperplane, which is a term given for plane dimensions both. And 4 things you can plot. So let's say from the hyperplane, what they essentially do is we have some extra space after this hyperplane, and this space is given by epsilon. So that's a normal SVR, and what we learned is since you could have some extra slack in the thing or some extra outliers outside this points, we introduced two more new variables, p and q, one on each side, and this is called slack variables. Essentially, it's like a new epsilon plus p and a new epsilon plus q, but you get an extra term in your loss function, which is L, which is C into P plus Q, and C forms a hyperparameter. And this is typically what we give in the SVR function as well. So of course with any SVM-like thing you have few constraints. For example, the difference in the predicted and the actual value must be less than or equal to this epsilon plus the max of P and Q. Obviously you cannot go past the gray lines. And also these P and Q should be greater than or equal to 0 because they extend outside this epsilon boundary. And we can also have non-linear fit too, and that's what's known as kernel. So we learned that there are a few kernels called RBF and all, RBF and linear and such things, and RBF is apparently some kind of normal approximation. So we tried out support vector regression. We actually didn't get much better results than polynomial regression, but it's something new and we enjoyed trying it. Next thing we did is stochastic gradient descent, which we learned is pretty much gradient descent, but the fact is gradient descent takes a very long time, as you have some matrix multiplications, and then you have to take for every single data point and every single column, which takes a long time. So SGD basically randomly selects either data points or weights to reduce or increase in that particular iteration, and so it converges faster. We tried this, and we also did something known as gradient boosting at a very high level. What we learned is it's essentially like adding something to a binary tree. So we have to see if, for example, where to add it, or if the key already exists. That kind of analogy could work here. So let's say if you had let's say a binary search tree, and if you were to add let's say 15 to the tree, we wouldn't because 15 already exists. But if you were to add 20, we would. So with that analogy in mind, we have a simple model, and then we have an incremental model. So simple model will be this part, and the incremental model will be this. And we choose to add it if it actually does something good for us. So it's more like a greedy strategy where you do local optimization at each step. They have some different kind of scoring mechanisms like Gini. We just learned that we have alternate scoring mechanisms, and also this gave us our best results, although we didn't actually give it for Kaggle submission, as in for the best 2 or 3 models, because we learned that it's not supposed to be used in this thing, but it was nevertheless a fun experience learning about this very nice technique, and I'm sure we'll use it in the future. The next task was classification. We had a lot of columns, so we had to do a lot more data analysis on this. So first thing, like before, we used box plots and histograms and also KDE plots to remove the nulls and the outliers values and the duplicated. And then we managed and manipulated some of the data types and removed some unnecessary columns as well. This took quite a sizable portion of the notebook. And then we removed, since there were so many columns, we have to remove the number of columns so as to make our models faster. So we removed columns with low variance and high correlation. And then we pass it to what's known as the SMOT algorithm. This basically uses synthetic data. I will explain that in a moment. Then much like on regression, we tried standardization. Although this didn't get better results, we tried it still. And then we split into train and test. And now on train, we tried three models: logistic regression, naive Bayes, and support vector machines. Although we tried this, although we tried all three, this one gave us the best results, and we continue to optimize on this by trying different combinations of EDA. For example, we replaced standardization with no standardization, removed some of the columns, put them back, and so on. Now, a brief note about SMOT. What this essentially is, it's a Python module that we imported and used. It stands for synthetic data of minor. It doesn't stand for synthetic data, but this is what I paraphrased it to be essentially. So, for example, in our data set as well, it was almost like a 6:1 split of, let's say, column 0 or 1. I wasn't sure exactly what the number is, so for sake of brevity, let's keep it as A and B. So if you have something like this, your results could be very biased because if it's considerably larger, even random selection will make for a very good model. So obviously, you have to do better. So we can either do one of three things. So what is one thing is we can take equal number of A or Bs. So that's called undersampling, or else we can oversample this. So oversampling essentially means you're going to create more copies of Bs such that it takes approximately more or less the amount of As. That's exactly what we did. That's what SMOT does actually. So let's say pluses are more than minuses, as the initial minuses were red, let's say. So what SMOT does essentially is if a parameter theta A or theta A belongs to the minority class, let's say in this case minus for some whatever reason, what they do is essentially they take all the other things, all the other thetas, and they get some nearest neighbor. So they use k nearest neighbors model and get something, like 1, 2, let's say ak or whatever. Now between theta A and A1, so let's say theta A parameters are let's say 1 and 2 and A1 are 3 and 4, whatever reason, for the column values and so on. So essentially what they do is they generate a new point by making something like 1.523. So this is a new data point and that gets put into this, for example, this minus here. And so like this you can choose how many data points you want to put. Of course, it's not perfectly reasonable to oversaturate the minority class, but that completely goes against what we intended to do. And also it could basically become a lot of saturation or very constancy in the data, in which case when we remove the variance columns it goes. But in any case, this SMOT algorithm actually gave us much better results and we continue to use the SMOT algorithm. And then to train the logistic regression model, as mentioned earlier, we use something known as grid search. Essentially what this is like a for loop. So you could have many different hyperparameters, let's say H1 list, and then you have H2 list, and now you try for each one in H1 and then for each one in H2 you fit it. Obviously this wasn't a very smart approach and it took a lot of time, but we did get a few, at least with the smaller lists of grid search, just for the sake of brevity and just for the sake of trying really something new, we did get a few hyperparameters, and that's I think what is our optional model, optimal model. Those are the two approaches we took. We hope this is actually the second part in our report. Our textual report is already there and we have linked this video there. So hope you enjoyed the video. Thank you.